Welcome to my talk on this nice, lazy Friday afternoon. Hope you all had a good conference. So what we will be talking about today is backend technologies that hopefully you're not fully familiar with, and you might be able to get something out of this talk. Who am I? My name is Savvas. I'm the principal engineer for apps at ASOS. And of course, you can find like my socials and stuff in that QR code. I'll post links at the end, so don't have to worry about taking a photo at the moment. Who are we? We are ASOS. We're very fashionable, as you can see from the photos. That's exactly how I dress. And I have our quote here. Our vision is to be the world's #1 fashion destination for fashion-loving 20-somethings. So exactly the audience of this conference. So who are we and why are we here? Well, we are here because we're mobile developers, but there's a lot of backend technologies that we might not be super familiar with that I believe we should be because it helps our careers. So obviously, everyone, at least hopefully everyone, should be familiar with the words on this word cloud. They're kind of like familiar Android technologies, MVP, Google Play, coroutines, but maybe some of these technologies are not familiar to at least some of you. And you might think, well, so what? Why do I care? Why do I need to know about these technologies? Well, you know, we build apps for a living, true. But it is very frustrating when you speak with non-app developers, let's say in your company, and they don't really have a grasp of exactly what it is that we do. We've encountered this a few times at ASOS, where you speak with some business partners, and they are under the impression that we release software the same way that the web, for instance, team does. They don't understand that we do like a fixed cadence of releases. We ship binaries to people's phones. So there's like a lot of core technologies that people might not be familiar with, and it's kind of frustrating. Now flip this equation around, and you might be the cause of frustration for some backend people or some web people when they might be discussing about technologies that you're not super familiar with. It also breaks barriers when you're speaking with someone. It is nice to be able to speak the same language and understand each other. There's a few technologies that I want to go over. They're kind of like broken down into vague categories that kind of relate to each other. It's not an exact science, so we'll see how it goes. Let's start with something that should be familiar with at least a few of us here, because it is something that we are exposed to a little bit more directly. Caching. The quote here, you probably have seen this before. It's a very famous quote. Caching is difficult. You might think that it's an easy thing to pin down. What is it? Just keep things locally, don't fetch them from a network. Done, right? Okay. Well, this is a problem that I will have to keep fixing. Apologies for that. Right. So caching, yes. You might think that it's easy, but it really isn't. In my experience, I've interviewed a lot of people and a lot of really senior developers who have been doing this for like years and years and years, don't really grasp some of the more nuanced topics of caching, and I think it's a really important thing to be able to at least understand at a high level. So the most important thing that I think everyone should, at least, if there's one thing you should take out of this talk, is expiry headers. Why? Well, we're a front-end developer, meaning that we tend to basically fetch resources from the network and display them, and we want to cache those resources. Now, this is a fairly standard flow of like receiving resources from the network. You kind of have like your view tries to load a resource from the network, it talks to your model, however, like you might have a view model or a presenter or whatever it is. Your view model basically checks through a repository of something if you have this item in the cache. If you have it, you return it to the view. If you don't have it, you have to go to the network, get it. So you load the resource, you get the resource back from the network, you put it in a cache, and then you return to the client, so the next time you get it from the cache, right? Super simple. But what does that step mean? What does in cache mean? Like, how do you determine whether an item is in the cache? Obviously, the simplest solution here would be to say, well, okay, it's in the cache if it's literally in the cache. I have like some sort of map, LRU cache or whatever, and if the item is present, it's identified by some resource, usually the URL, and if it's there, I get it, right? That works, but it's not very flexible, because that strategy effectively means that you have this item in the cache forever. Do you want to keep this item in the cache forever? For some things you might, but for some things, probably you don't. Things like, images. You want to cache them for some period of time, for the most time, but you want to have some flexibility in refreshing them. Also, it's the type of image might be an important thing to note. Like, okay, displaying product images, for instance, for clothes, you might want to cache them for a long time, but your profile image, you don't want to cache forever because you could go to the website and change it, right? So there's a lot of nuances here about how to effectively, it's basically what is your caching strategy? When do you evict items? This is the key question here. So this really is the solution. It's the most flexible solution. Every caching strategy is valid in its own use case, right? You might want to cache things forever, and that's perfectly fine, but you have to understand that that is exactly what you want to do. 99% of the time, this is the caching strategy you want. You want the server to control when resources get invalidated. Now, that could be an image, Like I said, images are usually the thing you want to cache more, but sometimes like actual API responses you want to cache as well. And there's no one better to know when those caches should expire than the server. The server understands what you're requesting, and it should know when these items should expire. Back to the example of the images that I talked about. In our case, our image servers know that product images, we want to cache for, let's say, a day, because we might potentially want to refresh them. So maybe a day is a good enough time frame. But your profile image, we might want to cache for, let's say, 10 minutes. So if you do change it, it will only be invalid in the client for 10 minutes. Right. The point is that you don't have to know about these strategies. The backend needs to. This is the old school way of setting these expiry headers. There was literally an HTTP header called expires, which would give you a hard-coded date. And that hard-coded date told you when the resource was invalid. So your networking client, library, okay, HTTP or whatever, should in theory respect this out of the box. So if your server sends these headers, you don't have to worry about anything as long as you have configured a disk or some other cache in your client. That should just work. That's a little bit inflexible because it is a hard date, and there's no way for the server to potentially change its mind, let's say, afterwards, right? Let's say the server said that an image is cached for a few days, and then for whatever reason you want to change it. There's no way for clients that have already received the resource to be notified about this fact. This is the more modern one, and when I say modern, it's already been like decades, but the modern one. Couple of decades, I think. So cache control. The cache control is very flexible because it allows both the server and the client to control the caching, basically, dance. The most common subsection, it's basically like a cache control is kind of like a catch-all header for directives that live under it, right? So you see here I have a max age, and the max age is effectively similar to the previous header. It would tell you this resource lives for 604,800 seconds, right? Which I don't know if I actually put, I don't know how long that is. You can do the math. It is as inflexible as the previous thing. So this is the least useful one, but it effectively behaves the same way. Now, there's a huge list of directives inside that header. I'm not going to go through all of them. I have a link there that you can follow. It is an interesting read-through. Do go through them. But some interesting ones that I should call out are basically, well, before going to the specific ones, I mentioned that the client can also control the headers. It doesn't necessarily have absolute control, but the client can indicate to the server what it wants, right? So the client can send a cache control header with some of these subdirectives, and that page tells you which ones are valid from the client side to effectively indicate to the server what kind of things you want. You can say, send me this thing if it's changed. Send me this thing if it's, I don't know, stale for more than 3 days. There's a lot of things you can do. These are obviously just hints. The server will have to honor them and decide on what it wants to do. Again, more details in the page. And the second one, so the important subdirective here is the still if error. This is a very useful one that you can send. This is how you effectively have a client get network resources that have for things that have expired. But if there's a network error, you still want to display something to the user. So you can inject this header in your outgoing requests and effectively say, you know what, I need a new resource if the local one I have has expired. But if for whatever reason there's a network error, I don't want to just get an error. I want the one that is in my cache that is still stale. It's better to show to the user something rather than nothing, right? So this is how you do that. And speaking of REST resources, e-tags. Does anyone here know what an e-tag is? A few? Ooh, okay, way more than I thought, so that's a good thing. But again, obviously I was expecting a lot of people not to know what they are, because again, we don't really deal with them on a daily basis, but we probably should all be aware of what they are. An e-tag is effectively an identifier a unique identifier for, let's say, a version of a resource, right? This is the technical definition, blah, 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 is the don't worry about it. Like, it doesn't matter. What you should have in your head is that an e-tag is a unique resource identifier. So effectively, every resource has a hash version of it. When you request a resource from the server, if obviously the server supports e-tags, you will get this header back with it. And your networking library already should be aware of e-tags and should save them with the resource. So when you cache them, you also cache the e-tag with it, usually in some sort of database. Like OKHTTP, I think, uses SQLite behind the scenes to coordinate all these things, right? And what you do effectively is when you make a request, you say, again, is it in my cache? You look at your cache. It is. It hasn't expired based on whatever actually, it has expired based on whatever directive we used. And at that point, you go, OK, I need it from the network. But when you make the request, you also send the saved e-tag that you have with it. So you say, I need this request. I have a local copy that it's expired, and that's the hash of it. And the server at that point can say, you know what? The resource hasn't changed since the last time you requested. I still have the same e-tag for that resource. So instead of sending you the full, let's say, image, which is a few kilobytes or megabytes, it will send you back a 3 or 4 response saying that it has not been modified. And at that point, your network client will basically receive that response and will say, OK, I will have a new expiry response using the headers that we talked about, and it will just refresh the local copy, right? So it will make the stale resource basically fresh again. So this is the way to avoid requesting data that you don't really need to. And this is why you can have things like really short-lived resources as long as your server supports e-tags. So you can basically have your avatar image, for instance, expire every minute. That doesn't mean you'll be downloading the avatar every minute. It just means that every minute you'll be doing a network call to check whether that avatar has changed. Obviously, a minute might be too short for your use case, but the idea is that you control that, right? There's another reason why you might want to use e-tags, and that is mid-air conflicts. Have you ever considered what happens when both you and a coworker tries to modify, let's say, a page on your wiki at the same time? Right? Let's say there's a version of the document on the server somewhere. You start making some changes. You press submit. At the same time, someone else is doing the same thing, right? So this is the scenario there. Effectively, 2 clients make requests to the server at the same time, and the server has not managed to complete one before it receives the other. Or it has completed but has not made sure that the second client gets the new version, right? So what do you do at that point? Well, the server will basically have to respond to one of the 2 clients, usually the later client, with a 412 precondition failed, I think it's called, yeah. And the idea is that every document has its own version. You can think of it as an e-tag. Well, it is actually an e-tag. The if matches header effectively says, this is the version of the document I had when I was modifying it. So does the other client. So the moment the server modifies the document and the second client makes the request, the server could go, that's not the version that I had when you tried to modify it, so I will tell you that that's invalid. And this is usually how you get the little, like refresh button if you're using Confluence or some other document. When you try to submit a change, you can get a bit more clever, and like you have the server monitor what area of the document you're modifying if you want to be very clever. But in theory, the server will not allow the second client to modify it, and it will do so by using an e-tag. So that's all about caching. Well, a little bit. Show of hands again. How many of you know what a CDN is? Oh, OK. Fewer people than e-tags. Interesting. So a CDN is like, I'm certain that, again, 99.9% of you are using one without knowing. It's a content delivery network, right? The idea is that you have a server sitting in front of your server that is very good at delivering resources, static resources usually, to your clients. They have a distributed network across the world, and the idea is that whenever I make a request, instead of hitting your actual server, which costs you, CPU time or I/O because you're doing like, I don't know, disk reads or writes, you have a thing sitting in front of your server that serves you these requests faster than your server could, right? So, yep, it's like I said, this is the kind of standard flow for a CDN. You make a request, it goes through the CDN goes, I don't know what this is. So the CDN hits your origin server, which is your actual server, the thing that you're deploying. Your server does its thing, DB, whatever, CPU, sends it to the CDN. The CDN then caches this response, sends it to your client, so when you make that request again, the CDN intercepts it and sends it to you without actually hitting your server. Now, why are we even talking about CDNs? Because the way that the CDN does this all is through e-tags and caching, right? So effectively, you can think of the CDN as a caching layer, but on outside of your client that caches content for you. And again, e-tags and all the things that we talked about are basically part of this protocol. And obviously, this is the main technology used for web pages. You might think, oh, a web page, it's a simple thing, right? I hit www.mywebsite.com, and that hits my server, and I serve some HTML back. Yes and no. You can do that, but if you have 10 million people hitting your website daily, that's going to cost you a lot of money, and it's going to cause you a lot of problems. So what happens when you hit a website? Well, you get the HTML for the website back, but do you get the full thing, or do you get partial HTML? Well, what we do is when you hit asos.com, you get a pre-rendered static version of the website, which contains some products. Let's say you're searching for jeans, right? So when you search asos.com search query jeans, the response you get back is a cached version of the website cached on a CDN layer. And the reason we do that is because a lot of people search for jeans, and we don't want to keep hitting our database every time a request comes in to search for jeans. We search it once, and then we cache it on the CDN for some sort of time. You don't want it to be too long, obviously, because then you might get out-of-date results. So this all is kind of like a balance that your site reliability engineers will basically keep tweaking. So yeah, okay, you get a static version of the website, but websites are not static these days. What happens when you scroll to the bottom of the page? Well, this is where a combination of statically server-rendered pages, effectively, that's the keyword for the technology that we're talking about here, server-rendered pages, is a page that is rendered on the server and then served to you cached. But when you scroll to the bottom of the page, your page is dynamic enough to have JavaScript inside it to go, okay, I need to load more data from the server. And at that point, you make dynamic requests, which hit your actual origin, and you then populate the actual web page that you receive. So today, if you hit ASOS, you basically get a combination of a server-rendered web page and a dynamically rendered web page on the client. And yeah, the reason you do that is for cost, obviously. Like I mentioned, database access costs money, CPU, all those things. So you want to cache as much as you can. So yep, this strategy is basically called multi-layer caching. You have caching at multiple stages of a user request or a user journey. And we do it because it is very cost effective, basically. And it also improves speed performance. Like for instance, you only need one server or origin server, let's say in the UK, but you can have CDNs all around the world. So when someone in the US makes a request, they get it from their local CDN faster than your server could potentially respond. And this is the full journey here. I'm not going to go through details, but this is a combination of the two previous diagrams that I showed, right? So this comes all the way from the user all the way to the server database with all the caching layers in between. So you can think of basically the internet today is a giant web of caching layers, and that's the reason why that quote about caching being the most difficult problem exists, because it is a very complicated system, and if you do it wrong, it can lead to a lot of problems. So knowing how these things work, at least at a high level, is a good thing. Which brings us to web application and API design. You might, again, not care about this, but like I mentioned before, it's useful to know these things, especially when you speak with stakeholders in your company who might be specifically aware of web API technologies. So REST. Everyone probably has heard of the term REST. It stands for the representational state transfer. I always forget. REST is not really a hard-coded set of, it's not a protocol or a standard, right? It's a set of architectural constraints. There's more stuff that you can read on the link that I have. Basically, there's a lot. If you ask 100 people what REST is and how you should implement REST, you'll get 100 different responses. So I'm not going to go into the details of what it is and what it should be, but I'm going to go through a few points that are relating to REST that I think are not ideological. Like, it's not, this is how I think it should be. There are reasons why you should do some things in REST that I think will affect you, so you should be aware of them. So let's talk about HTTP verbs. You may have heard of the term CRUD, create, read, update, delete. The idea is that in REST, URLs, resources, are not verbs. What's the word that I'm looking for? Nouns. They're nouns. And verbs are the things you want to do on those requests. This may be a familiar set of URLs to you. If you see this in your company, like, I wouldn't be surprised. A lot of people do this. You have multiple endpoints, one for adding an address, for instance, one for deleting an address, all those things. Now, there's nothing technically wrong with this. This will work. But there are some problems with this. Like I said, in REST, verbs are the HTTP operations you do, and nouns are the resources. So instead of saying add address, get address, change address, you want to have a resource called address, and then operate on that resource, like this. So there's one URL, which makes it easier for people to grok also, like let's say you have 100 different resources. If every resource has its own set of like 4 or 5 URLs, you're now having an explosion of URLs, which is not really great. So this makes things easier to understand. And it also follows the patterns, which are not just good in theory. There's practical reasons why you should do that. Right, so having one resource that has multiple verbs on it, so a post, a get, a put, a delete, allows middleware that sits between your client and the actual server that does these requests, these operations, to operate in the spec of HTTP. Now, effectively what happens is when you perform, let's say, a get, there are some understandings about gets that middleware that you or even your company doesn't control that might short circuit some requests not making into your server. You may see some people you may notice some APIs potentially requiring you to do a get on an API that actually writes data to the server. That's because they're misusing some things and they're trying to get around some of the problems of middleware. So effectively, middleware understands that some of these operations can be done many times in a row, and as long as one of them makes it to the server, the other ones don't need to, right? So you might be saying, why is this request not reaching my server? That's because the middleware somewhere caught it and is not actually forwarding it to your server. So as long as you follow the standards, you'll be fine. Another common thing that a lot of people get wrong is query parameters. You might say, I know what query parameters are. I use them all the time. Did you know that they can be a security risk? Now, everything in a request can be technically read by, well, not middleware, because, of course, your requests are encrypted, hopefully if you're using HTTPS, but server that lives after the certificate part of your stack can read the request that's coming into the system, right? And a lot of the middleware that you deploy after that point will log these things to various logs. 90% of the software out there will log the entire URL, including the query parameters. So if you have a request that looks like this, that sends secure like data, you're not going to get them, like there's no risk for like man in the middle or anything like that, because the query part of a URL is actually encrypted. The problem is between the actual like entry point to your service stack and the actual server that receives the request, there's like hundreds of pieces of software that might be logging those out into plain text. Now this has happened in a very, very popular fintech company within the last, let's say, 10 years that I won't mention, where people would be trying to update their PIN, and they basically had some software somewhere that was logging that PIN in plain text. Now, this never leaked because, again, it was an enclosed system, but you never would really want to be logging things into plain text, right? So if you ever see this sort of thing in your company or anywhere you work with, just shout from the rooftops, this is bad. You definitely do not want to be doing that, right? So get your security people involved and sort this out. What you want to be doing instead is sending them into, let's say, part of the body or the headers. Headers are a little bit more, some software will log them out. Body is the safest solution because no self-respecting software will actually log the body in production. JWT, that's another piece of technology that a lot of you may be familiar with. You may actually have to deal with these things at some point. They're effectively JSON web tokens. They're mostly used as part of like OAuth operations, which we'll talk in a bit. But the idea is that they're just pieces of JSON. They're nothing fancy, but they're signed pieces of JSON. So what they effectively do is they look like this. They're usually base64 encoded, so you get a JWT. There's some text on the left that you can see, which you can decode. Now, there's two main types of JWTs. One is a signed, and the other one is an encrypted one. You're really rarely going to be coming across encrypted JWTs. most of the time you'll be hitting assigned ones. So assigned JWT is not encrypted. You can literally read it, put it in a base64 decoder, and you can actually read it, the entire body. The idea there is that they're just pieces of JSON that carry information, usually for login purposes, but they also contain a piece at the end, you can see here verify signature, that is effectively the public a part of a signature, effectively, that you can use to verify that the sender of the JWT is the sender that you actually expect it to be. Now, 90% of the times, you won't be doing this, which you probably should. Like when you receive a JWT from a server, you in theory need to verify that it's coming from the right place, and it's not actually being modified by anyone in between. But the most important thing for our purposes is the parts that are kind of like in the payload. There are some parts of the payload that are standardized and some parts that are not. You can put anything you want in there, but some fields are required. And those fields allow you to do OAuth. OAuth, there's like, again, 100 different variations, but at the high level, OAuth is a way for you to authenticate against the service without you requiring to send the username and password with every request. And the way you do that is effectively, instead of doing this, which we talked about before, sending your username and password, even if you do this securely, as in send it in the body, like I mentioned, you still don't want to do it like all the time, because in theory, the more you perform the same request over and over, someone in the middle could, in theory, be able to decode this. Even though it's encrypted and all those things, you want to minimize the surface area, basically, of your attack. So the way you do that is you only send this once. It's not magic. You still need to send the username and password to a service. But instead of the service basically saying, OK, that's valid, the next time you need something, send them again, it responds back with a token. Right? So you basically say, OK, I need to log in, so I send the username and password. The service gives you back a response saying, yeah, that's good. And well, usually sends 2 tokens back, but you could send only 1. And the idea is you use this token, and that's sent through a JWT, to perform further authenticated requests, right? So instead of sending username and password, you send this token. And this token is short-lived. It allows you basically to have an expired resource, like similar to what we were talking about before with resources being expired, the tokens themselves can be expired. And the expired information is encapsulated in the token itself. So when you decode that JWT, one of the fields in that token is an expiry date. So before you make requests to the server, the client can determine whether that token that it has is expired or not. So that saves you a request response journey. And it also, it makes things faster. So effectively what you do is if you have an expired token, you perform a request to the server to refresh that token. So initially when you perform that first login, the server sends you 2 tokens, 1 access token and 1 refresh token. The access token is the token you use to access resources, and that's short-lived, usually a few minutes, but depending on the service, it might even be a few seconds, or it might be a few days, right? It doesn't matter. That information is encapsulated in the token itself. So your client will save the token in the database, the refresh token in the database, and whenever the access token has expired, it will go access the refresh token. I shouldn't have used the word access there. It will take the refresh token and use that to refresh the token that has just expired, right? So the way that effectively this works is that you use this special token much less frequently than your access token. So if your access token gets compromised, that's OK. The server can just stop accepting it, right? So at that point, you'll just refresh it. So this allows you to do some things that are basically not really possible if you just use standard authentication. One of these things is that, I think this is that explains the diagram. That diagram explains the user journey I just told you, right? So this is how you refresh the token. You use the access token you had. Right, so a server can actually, on its own, invalidate a token before its time has come, right? So let's say there's a security breach. The identity server can go and expire basically all the tokens that are actually out there. So the next time you request a resource, all the clients will have to basically refresh their tokens. And if it's a serious breach, at that point you can basically invalidate all the access tokens, all the refresh tokens as well, and therefore actually force users to log in again. This allows you to perform journeys that you may have seen in sites like Google, where you can actually log sessions, remote sessions out. So at Google, you can go and press a button, and any connected device will effectively be logged out. And that's how you do it. You basically say, I'm going to invalidate all the tokens that the server has accepted, so the next time any client tries to do anything, it will effectively be forced to reuse the username and password. And of course, if you only use username and password for authentication, the only way to potentially do that is to invalidate everyone's password, which you really don't want to do, because then they'll have to manually create a new password, and this is a nightmare. You don't really want to do that. Changing gears completely here, let's talk about what happens when you go through a tunnel while you're trying to do something like purchase a pair of jeans, right? Now, this is a question that I ask in my interview process, so if anyone interviews with ASUS in the future, you know what to do. If you try to perform any kind of transaction and you lose network connectivity while the transaction is in flight, like going through a tunnel, there's a possibility that the server has received your request and is actioning it at the moment, but your client got an error. So from your client's point of view, you just failed to perform this transaction, so you saw an error message to the user asking them to try again. The server has actually performed the transaction and potentially cost user money. Now, there are mitigations to get that to actually happen that are not the ones that I'm going to be talking about now, but in theory, that's the main concept. Like, well, how do you make sure from the client's point of view that you don't perform the same transaction more than once? And it's not necessarily a very super important thing like money. You might think, well, I don't have to deal with payments, so I don't have to worry about this sort of thing. This sort of thing can happen in any transactional call, like writing a tweet. Well, I should probably refresh these slides with posting a toot, but anyway, posting something that is transactional. Now, the equivalent here is you write a tweet, you press send, you perform the actual HTTP post or put or whatever it is that you do. The server has received it. At that point, you lose connectivity. Your client says error. It will either retry automatically or present the user with a button. The server has actually received that message, put it in the database somewhere, and then it receives it again because the user pressed a button. So now you've tweeted the same thing twice, which can be quite embarrassing. So how do you solve this? Every time I ask this, 90% of the people try to come up with a really clever solution of, like, say, some sort of system that notifies the clients when the server has actually completed this, the transaction, or some sort of very complicated thing where you send other requests to check if the request that you sent before has been received first before you do it again. And then, of course, the question becomes, OK, what happens if that fails? The solution is much simpler than that. It's actually surprisingly simple. Remember our friend the e-tag? Well, this is not exactly an e-tag, but the idea is an e-tag is a unique identifier of a resource, right? So the same way with an e-tag, you effectively have a unique identifier for your transaction. This is usually generated in the client. You effectively go and say, OK, I have some sort of transaction that I want to perform, buy some things or write a tweet. You generate a UUID. Usually, you want that UUID to be somehow tied to the data that you're sending, because in theory, let's say with the tweet scenario, right? It fails, but the server has received it. The user leaves and then goes, you know what, I want to post this message, even though potentially I've seen that it was already posted. And you might want to perform another post, but slightly tweak the data. So in theory, you should be hashing the data that your transaction is made up of in a way that guarantees no hash conflicts. There's libraries out there that do this sort of thing. But for now, just think about a random UUID. You generate a UUID, and you send it with your transaction. So you get a network connectivity error. So as far as you're concerned, it failed. The server has received it. It saves it. And then you send it again. But you send it with the same UUID. So at that point, the server can go, I've already actioned this, and I don't need to do anything about it. Usually, the server will just tell you that it has accepted instead of okayed it. So instead of like a 200, you'll get a 204 or a 202. I can't remember at this point. It's a 200 range response. And your client will be happy, and you will have only done this transaction once. Now, this might all sound a little hypothetical, but this has actually happened. Again, an example that I'll pull out of reality is a very famous food delivery company had this problem relatively recently, where they had a mistake that would effectively return an error to the client, but in the backend, it would actually have processed this request, and the client would automatically retry the request up to 3 times, and effectively purchase the same set of food up to 3 times in a row. So people would basically get 3 orders sent to their homes, right? So this actually happens. So you should keep that in the back of your heads. If you're doing any sort of transactional stuff with your backend, in theory, your backend engineers will have thought of this and asked you to do this. But if they haven't, ask them why. So yeah, the idea of all this is called idempotency. And idempotency effectively means the possibility to perform an operation as many times as you want without it having any side effects. Well, only having one side effect the first time you do it, right? And a few REST verbs, well, HTTP verbs, are by design, should be at least idempotent, and some of them shouldn't. So gets are idempotent, I think, yeah, puts, deletes. Posts are not idempotent. So in theory, you should not be performing a post for things that you know should be effectively, like I said, performed multiple times, but only need one request. That's why you usually see puts for these sort of things. Anyway, more details you can see in the link there. Do read it. It's a very interesting area. Now, I know I'm not that much of a time. I think only have 10 minutes left, so we're going to kind of like rush through the next bit. I personally think this is very important and very interesting, service topology. Topology sounds like a scary term. It literally means shape. So this effectively means how are services deployed and how do they look like when they actually go out there. And again, this is not affecting you as a front-end developer that much, but being aware of these terms, like I mentioned earlier, is a useful thing. Now, you may have heard of the word containers. Now, newfangled technology, but very useful because this has not has the potential, it already has transformed the way that software is deployed across the world. Now, containers are called containers because they share a very similar functionality with real-world containers, which are basically boxes that you put on a ship, right? So when we moved trade in the world from like literally just ships that you would put sacks of things on to containerizing them, we transformed trade. When you request a little item to come from you from, let's say, I don't know, China, Japan, India, the States, it doesn't matter what box it gets put in, because that box will eventually get put into one of these containers, right? So the shipping company doesn't care what you bought. It knows I can load these boxes into my ship, and I've optimized this process. I have cranes that pick these up and put them in a certain spot. I know how many boxes I can carry. It's all basically optimized, and it's standardized. Any port they go to will have machinery to pick these containers up and unload them, right? In the past, you literally had people go on a ship and pick up boxes and move them out, which was very inefficient. So what physical containers have done for world trade, digital containers have already done for software deployment. And the idea is you don't care what technology you use for deploying a service. Did you use Java, Kotlin, Go, C#? Did you use Tom? I don't know. It doesn't matter what kind of like server deployment you use. It doesn't matter as long as it's inside a digital container. The digital container effectively encapsulates software that is written, and it follows a certain effectively public interface that allows software that knows how to pick these boxes up and put them in the cloud or in a physical box somewhere, but they know how to do this and they know how to connect them with other boxes. And that's the equivalence there. Now, these are the kind of like top level technologies you might have heard already. Now, Containerd and Docker are basically container runtimes. They're basically the software that actually executes these containers and runs your software inside them. And Kubernetes, which comes from the Greek word Kybernetes, which means captain, is the most common, at least, a piece of technology that orchestrates them, that takes them and puts them where they need to go, and like when one of them dies, knows how to spin up a new one and knows how to connect them together so they can talk to each other, all those things. And a core concept of this, behind this deployment strategy, is microservices, which is hopefully a thing you're all aware of. Now, going back to the way that we write software in the mobile app world, is we basically do this, right? We have one piece of binary that we ship, which contains all the piece of code that we have. You have your front end, your network layer, your database, everything is in there. If any of these pieces crashes, let's say you have an exception that you didn't really properly handle in your database layer, your whole app will crash, right? So you have to restart the whole thing. And this is a monolith, effectively. It's one thing that runs as one piece of software. It works for mobile, and like no one's recommending we use microservices for mobile, even though that's an interesting discussion that we can definitely have. But backend, not so much. You don't want let's say your search part of your website crashed. Fine, you need to fix it, but people can still go to the website, right? They can still make purchases. You want parts of your website potentially work. So the way you do that is you deploy different pieces of software that know how to talk to each other, usually through HTTP, and you deploy them separately. As you can imagine, deploying different pieces of software completely separately can be a nightmare the more components you have, and they kind of like explode exponentially, especially if they all talk to each other, right? And the way you do that is you have containers do the work for you. So you ship a part of your app in a container, and then you ask your orchestration system to deploy it somewhere. And part of that orchestration automatically hooks everything together to talk to each other. Right? You usually do that by deploying each microservice into a cluster. And the cluster is basically a collection of microservices that have internal communication between them. Right? This allows you to also do cool things like multi-region deployments. So in ASUS's case, we have, I think, 2 or 3 regions that we support. We basically, whenever there's a new version of, let's say, our homepage of the website, that gets deployed both in the US and in Europe. So when you search for something, even though you use the same URL, the network manager knows where to direct the traffic. So we have 2 separate clusters, and basically the system automatically picks the one that is closer to you, so you get faster responses. It also allows you to do failover. If for whatever reason the European one fails, because, I don't know, the data center that is hosting it has a fire, automatically the system will redirect all the traffic to the US one. So your request will be slower, but at least your experience will not have degraded. And yeah, the way that this happens is obviously through DNS, another thing that you might be aware of. DNS is the service that translates URLs to IPs, and every software deployment system has built-in DNSs at multiple layers as well. And it's kind of like the caching problem again. Within a network is partly defined by its own DNS. So there's a resolution service that says, hey, I have this thing, give me a physical, like an IP address that I can talk to. So from the outside in, you effectively say www.asus.com. There's a DNS that effectively, based on the region you're located, will redirect you to the proper cluster. And then inside the cluster, there's going to be another DNS that knows which actual physical container to redirect the traffic to. So there's literally just like a cascading set of DNSs that route the traffic to the actual machine that needs it. And the most important thing about all these things is that based on the orchestration framework, Kubernetes, for example, all these things are kind of like failure resistant. So if any part of the system fails, it just automatically knows where to redirect the traffic to. I say automatically. If I have any actual SREs in here, they would shout at me saying that actually requires a lot of effort to maintain. But from our point of view, it's magic. And this is, yeah, like I mentioned before, clusters. Effectively, you might hear the word cluster, and it sounds like a scary thing. A cluster is literally a collection of machines. That's all it is. It's a collection of machines, usually virtual, but you can have physical clusters made up of different virtual machines, physical machines, that effectively, from the outside in, you only talk to as one unit. And the cluster internally has mechanisms to manage itself, spin up multiple versions of a website for redundancy, and knows how to route the traffic between all those bits of software. And the way it does that is using traffic managers or ingress controllers. Ingress is obviously the incoming traffic. So effectively, every cluster has this little piece of software that sits after, obviously, the outside DNS that directs the traffic to it. And it says, OK, you want asus.com/search. I know where search is. I have these 3 virtual machines there that handle search. And it will route the traffic to those machines. And again, there's like multiple strategies for which one do I pick? Do I hit them all at the same time? Do I round robin them? There's all these things. And yeah, this effectively demonstrates that you can have the same top-level IP that looks like you're talking to the same service, but based on the path that you have, you might be talking to a service in a completely different continent. And all that's handled for you automatically. A load balancer is a special kind of version of a traffic controller. A load balancer is effectively a way for you to split your traffic evenly between multiple versions, well, multiple instances, I should say, of the same version of your software. If you have 10,000 people hitting your service at the same time, well, actually, these days, 10,000 is not that much. Let's say you have 1 million people hitting your software at the same time. You don't want everything to go to one deployed instance of your service. That will crash everything. So you have a load balancer in the middle that knows how to basically go through all the, let's say you have 10 versions of your software running, and it will just distribute the traffic evenly. So from the outside, it looks like you're talking to the same machine, but you're really not. Of course, then that raises the important question, what happens to your data? You know, if I'm talking to one machine here and you're talking to this other machine there, and we have to coordinate the data between them, how do we do that? If I'm logged in, right, say, I want the same data to back up the systems, right? And the way you do that, usually there's one version of, let's say, a database running inside a cluster. But if you have multiple clusters, you want to make sure that the data is synchronized between them. And that's why you have multi-primary replications. It used to be called multi-master replication. Effectively, this allows, it's a technology that basically allows two different versions, instances of the same database to synchronize the data between them. Now, they're a very, very, very deep topic that I'm not even, like, I wouldn't even pretend to be an expert in. But effectively, like if you use MySQL, it has its own master-to-master replication. If you use NoSQL technologies, they all have their own kind of way of doing that. Obviously, there's latency involved with this. You can't just have it always magically be in sync. But this allows you to have what is called eventual consistency. So I could be writing to this database all the time, and as long as I know that at some point the changes that I made will be replicated to another one, I'm OK. And you know, that's kind of like a decision that the architects of the software will have made. This is a useful one that you might hear in your company. If you don't, it's an interesting one to think about, called Chaos Monkey. This basically is a testing technique that allows you to literally throw a wrench in the live production system of your service. You literally go in and just unplug pieces of your entire, let's say, cluster, or like, in theory, you should have a system resilient enough to say, if any part of my stack fails, everything should work. So this is a way to effectively stress test that. You literally deploy this, and as long as the service always works, you can have this running at any point, randomly unplugging services from your entire stack. Now, we're not there yet, but you know, I'm pretty sure larger companies like Google and Facebook are. I would hope that they are. I have completely run out of time, I just realized. Sorry, I'm way over time. So I will just have a list of honorable mentions and then hit you with the slide links. This is there. Google these after the talk. They are quite interesting topics that are, again, kind of like interesting things, but not potentially not impacting you directly. And this is the point where you actually take a photo, because, yeah, these slides are open source. They're deployed on GitHub, and you can see them for yourself. Thank you very much, and apologies for all around.